Hello. In this video, we're going to look at some applications of polar form. In particular, we're going to look at how polar form applies to complex numbers and how this can speed up a lot of our arithmetic. Now, calculating powers for real numbers is relatively easy. If I ask you to calculate 3 to the power of 5, you do 3 times 3 times 3 times 3 times 3, which is 243. However, powers of complex numbers quickly become unmanageable. So if you were to try to calculate I plus 1, or 1 plus I to the power of 4, well, what that means is you have 1 plus I times 1 plus I times 1 plus I times 1 plus I. Well, we can do FOIL for the first one, so it'll be 1 plus I plus I plus I squared. And then we leave the other two alone. 1 plus I plus I plus I squared, so it'll be 1 plus 2I minus 1, because I squared is negative 1. And then 1 plus I, 1 plus I. So this will give us 2I. 2I. And then 1 plus I, 1 plus I. So that'll be, if we multiply that in, 2I plus 2I squared, 1 plus I. So I guess that'll be 2I minus 2 if we use I squared. And then if I FOIL this out, I'll get 2I plus 2I squared minus 2I. Okay, well, it looks like the 2i's cancel, thank goodness. And so I'll have a negative 2 subtract 2, so negative 4. Now, we could do that. We got negative 4 in the end, but that was not an enjoyable process. It took a long time, and you can imagine if this was to the power of 5 or even 6, how quickly this would become unmanageable. But let's try converting the number into polar form. So here's our number, z equals 1 plus I. So the radius will be the square root of 1 squared plus 1 squared, or root 2. The reference angle will be tan inverse of 1 over 1, which would be, well, tan inverse of 1, which is pi by 4, or 45 degrees. Right, again, we could think of drawing this if we wanted. We have our little diagram, over 1, up 1, so there's our point. Now, if we're going to do this, we have, well, z would be r, and then cos pi by 4 plus I sine pi by 4. So if we want to calculate 1 plus I to the power of 4, that means we have to calculate z to the power of 4, which means we have, well, root 2 times cos of pi by 4 plus I sine pi by 4, all to the power of 4. Well, that means we'd have root 2 cos pi by 4 plus I sine pi by 4 times root 2 cos pi by 4 plus I sine pi by 4, and, well, you get the picture. This isn't necessarily helping either. So what else could we do? Well, neither rectangular form is the 1 plus I business. So neither rectangular form nor polar form, which was root 2 cos pi over 4 plus I sine pi over 4. Neither one of these forms made calculating the power particularly enjoyable. If only there was some third form for a complex number. And indeed there is. We can use what's called Euler's formula. So Euler's formula comes from a very famous mathematician, Leonhard Euler. You can look him up. And he developed this wonderful formula, that if you have a complex number in the form r cos theta plus I sine theta, you can convert that into, well, the r will be there, but e to the I theta. Apparently, if you have a complex number in polar form, you could rewrite it as a e and then I and then theta. This is called a complex exponential. So this is called, for a complex number, exponential form. Well, okay, it seems kind of weird, but let's see how this would work. Well, 1 plus I is equal to root 2 cos pi by 4 plus I sine pi by 4. And Euler's formula gives us root 2 e to the I times pi over 4. Well, that's kind of a strange formula, but we're going to trust him on it. We're going to trust that this is true. And in later math courses, you'll prove that this formula is true. But for now, we'll trust that Euler figured it out correctly. How would this work for calculating the fourth power? Well, 1 plus I to the 4 would be equal to root 2 e to the I pi over 4. And we would raise this thing to the fourth power. Now, if you remember your exponent rules, the 4 powers the root 2 and the 4 powers this, because they're both being multiplied. So we get root 2 to the 4 times e I pi over 4 to the 4. Now, root 2 to the 4 means root 2 times root 2 times root 2 times root 2. So you have 2 of the root 2's grouped together and 2 of the root 2's grouped together, and you just get, well, 2 times 2 or 4. Another way of seeing this is this would be 2 to the 1/2 to the power of 4, which you could write as 2 to the 4 over 2, because when power to a power you multiply, which gives you 2 to the 2 and just 4. But that gives us a great idea. What if we did the same thing over here? This is power to a power, so we could multiply. E to the I pi over 4 times 4. All right, so we have 4 times e to the 4's cancel, and just I pi. Well, let's now use the formula to convert back. The formula says that if I have e to the I theta, I could convert it back, put the r in front, and put cos theta plus I sine theta. So I'll get 4 times cos of pi, because here we can see theta is equal to pi, plus I sine pi. And let's use our knowledge of angles. Cos of pi is going to be -1. Sine of pi is going to be 0. And so I get 4 times -1, which is -4. Hey, that's the same answer we got before, but this time we didn't have to FOIL and FOIL and FOIL. We just used Euler's formula. And so with exponential form, all sorts of amazing areas of mathematics become possible. For example, instead of doing division, we could actually just use exponent rules. So if you remember from our work we've been doing, 1 plus I is equal to root 2 e to the I pi over 4. So if we have 1 over 1 plus I squared, we could write that as 1 over root 2 e to the I pi over 4 squared. Because if we wanted to do this properly, we'd have to FOIL this out and then multiply by the conjugate and clean it all up, and it would be a fair bit of work. But let's do it with this exponential form. Well, we know from exponent rules that 2 will square the root 2 to give us a 2, and power to a power will multiply, so e to the pi over 4 times 2. So e to the I pi over 2. Well, now exponent rules tell us that if I want to move this to the top, I have to switch the sign. So I'm going to write this as like a half e to the negative I pi over 2. So that will be 1/2 cos of negative pi over 2 plus I sine negative pi over 2. So again, use your unit circle knowledge. Cos of negative pi over 2 will be 0. Sine of negative pi over 2 will be -1. And well, there's our answer, negative I over 2. Again, no conjugate required, no foiling required. We just really get to use exponent rules and use our knowledge of the unit circle. And so we can speed up our multiplication. You would never want to do a question like this by hand. I plus 1 plus I to the power of 5 and 1 minus I to the power of 3. You'd have to FOIL this out and expand it all. It looks absolutely horrible, but it's going to be not too bad using exponent rules and our exponential form. Now, we do have to convert this 1 plus I. We need to convert that into some type of exponent form. We don't have exponential form for that. We do for this one. 1 plus I will be root 2 e to the I pi over 4. We've been working on that for a few questions, but we should convert this one over here. So we draw a little diagram. Over 1, down 1, so right about there. Radius will be 1 squared plus 1 squared. So same radius, root 2. Now we can find the reference angle. Will be tan inverse of 1 over 1. So it'll be pi by 4, which means the angle will be 2 pi minus the reference angle. So 2 pi minus pi over 4. Or you might have just been able to tell from the diagram right away. The angle here we could write as 7 pi by 4. So that means our 1 plus I is going to be equal to, well, we'd have our r and our theta. So let's just keep this off to the side. This would be root 2 e to the I 7 pi over 4 to the power of 3. All right, now let's try to work on this math here. Well, the exponent rules give us root 2 to the 5, e to the I 5 pi over 3. Because we need to multiply that 5 in, so you kind of have 1 pi over 4, so you get 5 pi over 4. Times, well, the root 2 to the 3. And then e to the I, 7 times 3 will be 21. So 21 pi over 4. Now again, using exponent rules, we can go ahead and group these two because everything is multiplied together. And we'll put these two next to each other as well. So we have root 2 to the 5 times root 2 to the 3 times e to the I, 5 pi over 4 times e to the I, 21 pi over 4. So root 2 to the 5, root 2 to the 3 will be root 2 to the 8. And then e to the 5 pi over 4 and 21 pi over 4 will be e to the I. Well, 21 plus 5 is 26 pi over 4. Now root 2 to the 8, well again, you could think about that as 2 to the 1/2. And over here we should probably reduce this fraction to be 13 pi over 2. So that'll be 8, and half of 8 will be 4, so 2 to the 4, which will be 16. We have e to the I, 13 pi over 2, e to the I times 13 pi over 2. Now it's important that we eventually convert this back into polar form so we can figure out what the actual value is. Exponential form is good for doing the arithmetic, but we do need to get the cos and the sine for doing the unit circle values. So 13 pi over 2 plus I sine 13 pi over 2. Well, it looks like we need the skill of finding a coterminal angle from pre-cal. 13 pi over 2, we can imagine that on a circle. So this is 1 pi, and then 2 pi, and then 3 pi, and then 4 pi. Well, we should maybe think about how much is 13 pi over 2. So 13 pi over 2. Well, 2 goes into 13 6 times, so it's 6 and 1/2 pi's, if we write it as a mixed number. So back to our circle, we had 1, 2, 3, 4, 5, 6. So that's 6 pi's, and then 1/2 pi ends us right here. So right at the top of the unit circle, 6.5 pi's is where we get. And so thinking there, sine of 13 pi over 2 is going to be equal to 1, and cos will be 0. So 16 times 0 plus I times 1, which gives us our final answer of 16i. And again, we're able to find that answer quite quickly without having to do any foiling, any math of the FOIL and the multiply and the complex numbers. We really just use exponent rules and our knowledge of trigonometry. Now, believe it or not, exponential form actually allows us to unlock the truths of the universe. For example, you might remember this identity from pre-calc. Cos of a plus b is equal to cos a cos b minus sine a sine b. Why is this identity true? Well, there is a proof from Khan Academy that shows this using some complicated triangles, and that is one proof. But I want to show you another proof, a proof that I think is more interesting and ultimately more satisfying. So what we're going to do is start with this expression, cos of a plus b plus I sine of a plus b. So we have cos a plus b plus I sine a plus b. And we're going to convert it into exponential form. So the radius here is 1, it's invisible, so we don't have to write it. We have e to the I, a plus b. Let's go ahead and expand that as e to the I, a plus ib. We'll use those exponent rules in reverse, so e to the I, a times e to the I, b. Now, I'm going to convert this back into polar form. Cos of a plus I sine of a, cos of b plus I sine of b. Now, we haven't done any foiling in a while because we've been staying away from it, so just for fun, let's go ahead and FOIL this out. So we're going to get a lot of terms here. We've got the cos and the sine and the sine. We're going to FOIL all that out. So we get cos a cos b plus I cos a sine b plus I sine a cos b plus, well, there's an I squared there, sine a sine b. Now, this I squared, whenever you see I squared, we know that's negative 1. And so I'm going to put this term over next to this term because this is going to be a real number because it's a negative 1 and this is a real number and these two are imaginary numbers. So we're going to put those at the end. So we'll have cos a cos b minus sine a sine b plus I'm just going to reverse the order here, sine a cos b plus I cos a sine b. And now I'm just going to, if you notice, we have this I in common, so I'm going to factor it out. So that'll give me, the other part's still the same, cos a cos b minus sine a sine b plus I sine a cos b plus cos a sine b. Well, let's take a look. We started over here with a number that had a real part. This right here is real. And it had an imaginary part. We ended up, after doing some math, with a number that has a real part and a number that has an imaginary part. And the way it works with complex numbers is that if you start with a number and it's all equal the whole time, well, the real parts should be equal to each other and the imaginary part should be equal. We didn't do anything to this. It was equal the whole time. And so this real part on the left-hand side of cos a plus b must be equal to this real part over here of cos a cos b sine a sine b. And this imaginary part up here of sine a plus b must be equal to this imaginary part of sine a cos b and cos a sine b. Well, but that tells us then, based on the real part, that cos a plus b must be equal to cos a cos b minus sine a sine b, which is our identity. And based on the imaginary part, we have sine of a plus b equal to sine a cos b plus cos a sine b, which is incredible. We're able to come up with these identities almost by accident, by just using some exponent rules and then foiling it out. These identities just mysteriously appear almost out of thin air. And last but not least, if we use r equal to 1, theta equal to pi, we arrive at possibly the most beautiful equation in mathematics. So we have 1 here, e to the I pi, and we convert that to be cos pi plus I sine pi. Cos of pi is -1, and sine of pi, of course, gives you 0. So you get e to the I pi equals -1, and if you move the -1 over to the other side, you have e to the I pi plus 1 equals 0. Here we have the use of the famous number pi, the famous number e, the new to you but very famous number I, 1, which is the first of the counting numbers, and 0, which is in some ways the middle of the number system. It's a very, very important number. 0 took a long time for mathematicians to invent, and to have all of these numbers combined in this formula, it's just something remarkable. To have pi and e and the number 1, to have all of this culminate in this identity, it's a thing of beauty. So I just encourage you to pause the video and stare at that identity. Let it sink in. It's a very, very famous mathematical identity. If you go ahead and Google it, it comes up. There's a lot of art done around it. Sometimes people even get this tattooed. It's just a very famous and wonderful identity in mathematics. So make sure you try some exercises with the applications of polar form. There's some examples here where you can convert, where you can do some easier problems with the exponential form. Make sure you do number 1 carefully and check your answers, because you'll be using the answers for number 1 in some of the following questions. And as always, thanks for watching.